Good evening, everybody, and a very warm welcome to IF Oxford, the Science and Ideas Festival. Tonight's talk is the past, present and future of fusion energy in Oxfordshire. It's an incredibly dynamic area of research at the moment. There's a huge amount going on around the Culham Science Centre, where the United Kingdom Atomic Energy Authority is based. And we're very grateful to the UKAEA for sponsoring the festival this year. Tonight's speaker is Chris Warwick. He worked as an experimental physicist at the Culham Science Centre for over 10 years, starting in 1990. But now he's part of the communications team and he is outreach and student placement manager. So he's seen fusion energy from sort of both sides, from actually working in experimental physics, but also in helping new people to understand the technology that's being developed right now. I'd love to introduce you to Chris and pass over to him to take us through tonight's talk. Chris.
Thanks, Kathy, that's brilliant. I have quite a lot of slides and I'm going to canter through them pretty quickly to give you a chance to ask questions at the end. I'll try not to sidetrack myself. So the title agreed was the past, present and future, and I've split into three sections, but I'm going to talk to you first of all about what fusion is and why we do it, because a lot of the rest of the talk will be on why it's really difficult to do. In many ways, fusion is the holy grail of making electricity in the future. Little or no environmental impacts, low carbon certainly. So it fits very much as we see it with renewables and probably advanced fission. If you have fusion and advanced fission and renewables in the future, then I think that's going to be as good an options as you're going to get. You're going to need as many options as you can. Unlike fission, the fuel, the radioactive elements of the fusion process are within the structures of the machines, not from waste products per se. The waste product is helium. I'll show you that in a second. We will activate structures depending on the fuels we use, and I'll talk to you about that in a second, including tritium, but also depending on the materials we choose. As far as we think we might produce structures as long-lived as a few hundreds of years, that is nowhere near as active for as long as some of the fissile waste, of course. Not to be dismissed, but nevertheless an advantage. This one is easier to justify. You cannot have a runaway reaction in a fusion reaction. It's frankly so difficult to get going, it'll always stop itself, and I'll try and explain that as I go through. And the fuels, one of which is deuterium, is available freely in water. So 1 in 6,000 water molecules is deuterium, and we have an awful lot of water on the Earth. The other one I haven't mentioned here is it's an incredibly efficient process. You need very little fuel to get yourself going, but fusion is really difficult. Fusion is what happens in the sun. It's what makes the sun shine. Every star you see in the sky tonight, nice clear night, is a fusion power plant essentially up in the sky. We are trying to make that more efficient and make that happen here on Earth in many ways, make a miniature sun inside a power station. The center of the sun is at 15 million degrees C. The gas of fuels is at that temperature, meaning that the hydrogen in the sun is moving quickly enough to stick together and fuse. We actually need, with the reaction we choose, I'll tell you that in a second, around 10 times hotter than the sun. So many of the challenges here stem from the fact that we have to heat our gas of fuels to 10 times hotter than the sun for fusion to start to occur. We need a balance of it, getting it as dense as possible, as hot as possible, and as well confined as possible. The reaction we choose, unlike the sun, which is a very inefficient reaction in many ways, is of two heavy forms of hydrogen, deuterium and tritium, heavy hydrogen and super heavy hydrogen, which at the conditions of around 150 million degrees C will stick and irreversibly make helium. That's our waste product. So we will use that within the plant to cryogenically cool things, for example. And a spare neutron, both of which come out with more energy than the deuterium and tritium came in by dint of the binding energy within the nucleus. Helium needs less energy to bind it together, energy gets released, lots of energy. So that's what fusion is all about. That is the reaction that we are striving at UKAEA and at many other labs around the world to get going. So looking at the title of the talk, I'm going to talk to you a little bit about the past. I have a particular interest in the history of fusion research. So I'm going to canter through starting in 1920 with this gentleman, Sir Arthur Stanley Eddington, who stood up at the 1920 British Association Festival of Science and proposed that indeed it was fusion that was making the sun shine. People had been postulating in the 1800s exactly what might make the sun shine, with all sorts of different suggestions. By starting to measure the wavelength of light coming from the sun, Eddington postulated that it was indeed fusion going on. And this was his rather prophetic quote at the time. I'm going to read out the very last bit. It's this latent power for the well-being of the human race or for its suicide. We are very much for the well-being. We are only pursuing fusion to make electricity in the future and contribute to a low-carbon future economy. We are not interested at all, and none of the science we do is relevant to the other type of fusion, of course. So what happened then, 30s and 40s in particular, and very much concentrating on Oxford. There was work going on all around the world, but the UK was certainly a hotbed of fusion research historically as well as now, and indeed Oxfordshire as well. So Oxford University started to design machines that look a little bit similar to the machines we have today. This is a circular pinch type device where you put a gas in here, broke it down with a large voltage through it, fed a current through it, which made a magnetic field which helped pinch it away from the walls. Very, very small, these experiments, but started to understand some of the fundamental plasma physics, plasma being this hot gas of fuels that we create. So these were done by Peter Toneman in particular at the Clarendon Laboratory in Oxford. The story really starts after the Second World War with the formation of the United Kingdom Atomic Energy Authority in 1953. And they built one of their centres around the UK was at Harwell, the Atomic Energy Research Establishment, which had been an RAF base. Indeed, some of the D-Day paratroopers took off from Harwell, amongst many other sites in the south of England. There's a rather iconic picture of Harwell back in the day, probably taken either from a plane or up on the Ridgeway, I would guess. And part of the work they did, most of the work they did there was in fission research, but part of the work they did was in fusion in the rather magnificently titled Hangar 7. So that's really where the story starts with any kind of energy and gusto. And before I get on to the most famous experiment at Harwell, it's worth mentioning one other big event in the UK that really did turn the tide for fusion a little bit at the time. Kurchatov was the big Russian fusion guy. Of course, straight after the Second World War, the Cold War had started. We had really no idea what fusion work was going on the other side of the Iron Curtain. Nikita Khrushchev, the Russian premier at the time, came to visit the UK in really quite a landmark visit. And he brought his fusion guy with him, and the Russians request, they decided they wanted to come and visit Harwell. They wanted to come and give a talk. So Kurchatov came to give a talk at Harwell, outlining the kind of work they were doing. And this was met with real interest because we just didn't know what they were doing. They outlined the kind of work they were doing, which in some regards was more advanced than the work we and in the West were doing. And that was met with real surprise and started at least the process of declassifying this work. At Harwell, the work was linked to weapons research, but it was decided that the link was so tenuous that really, and the fact that we were on similar lines to the east as well, then we really may as well declassify and ultimately move to the Cullen site that I'll describe in a minute. The most famous experiment at Harwell was Zeta, Zero Energy Thermonuclear Apparatus. There is a picture of the Zeta machine and a rather magnificent picture of the Zeta team. Not very good for diversity, I'm afraid, but this was 1958-59. So you can date it by many of the scientists there holding pipes in their hands. Some pictures of the Zeta control room. This is all very much analog at the time. This was not quite a tokamak. I'll come on to what that is in a second, which is what we're running at the minute. It was more of a pinch experiment, similar but much bigger to the kind of things they've been doing at Oxford. Added magnetic fields to help with instabilities, and this was an incredibly successful experiment, pretty much the biggest in the world at the time. So we were leading the world. They started to see some neutrons quite quickly, and that got everyone really very excited about what Zeta was going to be able to do. And here is a picture of one of the very first outside BBC broadcasts at Harwell. as we announced what at the time was thought to be fusion from within the plasma. So, this was really very exciting. This was January 1958. And there is I've got most of these newspapers. There is a picture of the newspaper at the time. I don't know which newspaper this was, I'm afraid. And you can see some of the headlines here. This was huge pride in the UK. If you can picture back to the scene, Sputnik had just gone up. We felt rather ill at ease in the West, and we really needed to feel proud about something. That there was very much a focus on the fantastic British scientists that were looking into this, the brains behind the Triumph, if you can see there. The one that amuses me, 2 headlines down, is electricity would be, and I quote, too cheap to charge. I wish I could say that today. Nothing is too cheap to charge. And several months later, they discovered the neutrons that had just been local neutrons. They hadn't been from the bulk of the plasma, and various retractions occurred. The decision to declassify really brought to pass that a new site should be found. The universities, Aldermaston indeed was doing fusion research, and Harwell, all pushed their work onto one brand new site at what was, at the end of the Second World War, a Royal Naval Air Station at Culham. And I could talk to you all about the planes that flew, but that's not why you've come to listen tonight. There's a mosquito flying just over the crowd line at one of their air days. In 1953, RNAS Culham closed. It ended up being an Admiralty sort of depot, really, and storage site, and a satellite of RAF Abingdon for a little bit, but ripe for us to take it over as a fusion site in 1962. And by 1965, Culham Science Centre had been opened. Various experiments in the late 60s, early 1970s. What really put Culham on the map, of course, was the decision to host Europe's massive experiment at the time, still running today, the Joint European Torus at Culham. I'll tell you what JET is a little bit later on. So there's some pictures of the construction in the early 1980s. This was a machine 100 times bigger than anything that had been operated before, and a true tokamak, a device with much more external magnetic field around a toroidal or ring-shaped chamber, the magnetic field designed to hold in and confine the very hot plasma in place so it doesn't touch the walls. Some more pictures of the construction of the actual JET machine. And there is a more recent picture from above. It's evolved enormously over the 30 odd years we've been running it, and still is the biggest machine around. First plasma 1983, I always show this picture because I was 16 in 1983. I know I don't look that old, but there you are. There is a picture of everyone looking at an ammeter connected to a coil around the JET plasma that marked the very first plasma on JET, June the 25th, 1983. Why are they all looking at that ammeter not in a fancy control room full of computers? Because those were computers in 1983. I can remember at 16, 15, getting my first ZX Spectrum and being delighted my parents could afford a 48K one. Beneath it, I think, is a Commodore 64. So there really was very little computing around. And when you compare to what we now use in the way of computing control of JET, it's quite astonishing how far things have evolved. Two of the final slides really on where we got to in the 90s, UKAEA, as well as operating JET for the wider European fusion community, we started to really look at more compact devices. So not so much a great big ring shape than more of a donut or car tire, but more compact, a bit more like an apple with the core taken out of, inherently more efficient, with certain disadvantages, but ones that we battled to overcome, but that could point the way to a more compact and potentially more efficient source, a power plant in the future. So that's a bit of a pointer to where I'm going to go. The present, it was relatively easy. I talk about the present all the time. So there is the Culham site now. I'm just going to show you, we're a bit big on acronyms at UKAEA. So I'm just going to go through these very quickly with a slide or two on each. We host for Europe and operate and provide all the engineering support for the Joint European Torus. We have our own UK experiment called MAST, Mega Amp Spherical Tokamak, along that more compact route that I just described. Recently upgraded, 7-year upgrade to the machine, MAST upgrade, or MAST U. We have a burgeoning and very quickly and rapidly growing technology set of suites and facilities, including a materials research facility, MRF, looking at materials for future power plants. A robotics center, you need to be able to remotely maintain these devices. That's race. And understanding we need, as we build all these facilities and recruit, we need to train as many staff as possible. So an apprentice training center, Oxfordshire Advanced Skills. We also host many other scientific companies on the Culham site. There is an interior picture of JET to give you some scale. This is about 5 meters high by 2 meters across, about 90 cubic meters. You worry about the plasma contacting the walls, so you have protective tiles of beryllium and tungsten on the inner and outer walls. And on the right-hand side, left-hand side there, you can see one of our robotic arms. JET is unique amongst world fusion experiments, in particular world tokamaks. It's the only machine with a full remote handling capability, the only machine that can use tritium as well as deuterium, tritium being radioactive. So we deal with it very carefully, but we can and are using it. So there's another couple of pictures of JET, a pretty poor photograph from above, showing you, if nothing else, the complexity of the machine and all its subsystems. Another one underneath to give you some sense of scale, with a standard European person stood next to the machine to give you a sense of how big it is. It's a genuinely big piece of kit. Remote handling, as I say, absolutely unique, based on a person in the loop system. So you can see on that photo, someone controlling a pair of mechanical arms. And when we are doing a big maintenance period, typically 6 to 8 months inside the machine, changing tiles over, installing new diagnostics, whatever we might be doing, then we'll do it pretty much all remotely. The operator controlling the arms, the other end of the arms you can see here inside the machine, doing pretty much anything the operator tells them, with force feedback between the two. Fusion is in many ways entering the delivery era. This is a picture of not something in Oxfordshire. This is a picture of the south of France, where the international ITER experiment is being built. A power plant scale machine, not going to generate electricity, but bringing all of the engineering together from partners all around the world, the EU, China, Japan, the US, Russia, India and South Korea, all joining forces and all building bits of this device that will start up in the next few years and will, for the first time, produce for periods of an hour or more, 10 times more fusion power out than in. JET has not and will never produce more power out than in. It can produce fusion, but it's not big enough to produce more power out than in. At Culham, over the last few years, I mentioned these technology facilities. We've taken a really hard look at what a power plant needs in the future. And there are 6 main things. You need to be able to heat this plasma to 150 million degrees C and hold it there. You need to understand how to exhaust heat out. It's almost too good, the magnetic field, at holding the heat in. So you need to bleed out and exhaust excess heat. That's something our new Mast upgrade machine is doing with this compact design. What do I make these devices out of? That materials that are robust to those very fast neutrons that will bombard them, but also won't get too active from the action of the neutrons. How can I work with industry to test and validate components, technology and manufacturing? How can I make sure I have a fuel cycle that works properly? How can I breed the tritium from a blanket of lithium? I'm not going to have time to talk too much about that, but that's one of the key technology areas. And absolutely critically, how, when I need to, can I get a robot in quickly, change something and get out so that I'm generating electricity for most of the time rather than down doing maintenance? All of these are practical issues for a power plant. The question, therefore, is not, can I make fusion work? The question is, can I make fusion work economically? And the right materials, the right validation, the right fuel cycle, the right robotics, all of that matters. It's more engineering and technology that we're focused on now than the actual plasma physics. We sort of get that bit. Now the rest is, how can I build a device that works and works economically? And we have new centres looking at most of these. So starting off with Mast Upgrade, our more compact machine, based on this expertise we have in more compact tokamaks. I'm not going to have a chance to talk too much about how we exhaust out effectively this exhaust power, but we are devising an exhaust system that does not have heat loadings typically in exhaust systems of something like an arc welder, but more like a car engine. So we have reduced the power loadings right down, which should mean we have to replace those exhaust system components much less often. There is a photograph of the upgraded mast. RACE is our robotics centre. So a picture at the top. It's since been actually extended at the front to house even more meeting rooms and offices. We started off with RACE with 70 staff, and we're at close to 200 now, offering robotics expertise to many fusion projects, working with industry to win contracts on ITER, looking to future power plant designs, but with also an eye on where robotics can be used elsewhere. So we're not completely obsessed with fusion here. We may work with people for deep sea and space. That we're already working with the wider fission industry in terms of decommissioning and remote handling techniques there. Our materials research facility, which is a series of hot cells that can, we're not a licensed site at Culham, but can test, prepare and test very small active samples of material. So for instance, we could take a candidate material for a fusion power station, bombard it with fusion neutrons in various rigs around the world, bring that bit of material here to see how weakened it has become. And we can, on a microscopic scale, test material strength in our material research facility. And a new suite of facilities being built at the minute, looking at the fusion technology. So these are various testing rigs that will test components in realistic fusion conditions, again, working heavily with industry, and our new heat centre looking at all things tritium. One word just before I go to the future, and I'm very conscious of the clock, so I'm trying to keep to time. Bearing in mind the title of the talk was about Oxfordshire. We are obviously based in Oxfordshire. We do have a new centre up in Rotherham in Yorkshire, looking at some of our fusion technology facilities. But we very much recognise in the last few years that there are many others looking at fusion in Oxfordshire, and we are building with them a cluster of expertise. This is to do with collaboration, it's to do with sharing knowledge, to do with sharing talent around and marketing and messaging on a very high level what fusion can offer. Here are some of the other companies as well as us. Two new startups, First Light and Tokamak Energy. They're no longer startups. They get upset if I call them that. Mature companies now, based at Milton Park for Tokamak Energy and Begbrook Science Park for First Light Fusion. Tokamak Energy looking, as the name suggests, at Tokamak's First Light at something very, very different, but looking at how we can put fusion on the grid from a private fusion perspective. The Fusion Industry Association is starting to act in the US and in the UK with a little bit of one voice. And we are welcoming General Fusion, a Canadian company, to build a new facility here. You may have seen that announced back in the summer in the next few years. So for the first time at the Culham site, there will be a major private fusion company as well as ourselves and our work. So I think it isn't just us. I mean, I'm going to talk mostly about us, but there are many others in the Oxfordshire space. So the future in the last sort of 7 or 8 minutes I've got. And I found this rather difficult to write, and it was really useful for me to write it, and I'll come up with a major conclusion at the end, if I may. So in a number of areas, fusion is pushing ahead very quickly, and it is, over the last few years, for the first time, starting to look at the end product, what the actual power plants will look like. The UK, we have been lucky enough to secure UK government investment of 220 million in the last couple of years to do a project called STEP, or the Spherical Tokamak for Energy Production, a more compact device based on our expertise with First Start and then Mast and Mast Upgrade, to look at these more compact devices and look at how we can design one of these to go on the grid. This is designed to produce net electric. It is a prototype, it's not a commercial plant. We are midway through the conceptual design now, and we're looking at how we can integrate systems, how we can test steady state operation, how we can design components, starting to really understand what this machine might look like, how we can demonstrate breeding enough tritium from within the plant, how we can devise effective and quick remote handling systems. So this is a really exciting project for us. I talked about Oxfordshire. We have recently announced a down selection of the potential sites around the UK that might host STEP, and you'll notice that Oxfordshire is not in those. So STEP will disappear off at some point to one of these sites. That the 5 in the running at the minute are the 5 you can see there. So these are not in Oxfordshire, but I think one of the messages I want to give you is that Oxfordshire will remain very much a hub for a fusion cluster, regardless of the fact that STEP will disappear off into the somewhere else in the UK, and you know, over the next few years we'll decide exactly which of those sites will host it. Putting everything together a little bit, at the minute we're running Mast and Jet at Culham. ITER coming on stream properly and doing really high power operation in the early 2030s. STEP in the early 2040s is a prototype power plant turning turbines, generating electricity. Not commercial, but very much a prototype power station. And Europe's prototype power station, based more on the conventional jet ITER type of large donut shape of tokamak, is called Demo, hoping to come on stream in the 2050s. If I went further around the world, China with a very aggressive plan to build the Chinese fusion energy test reactor in the early 2040s as well, with active power plant programs in most of the other ITER partners. So this is in no sense just a UK European angle. There were many others around the world looking at power plants, and indeed some of the private companies looking at power plant designs as well. Very quickly, I spoke about general fusion. There is an artist's impression of what their general fusion building will look like, which will be based on the Culham site in the next few years. This is not a power plant, but it's a major significant facility for general fusion. Where does all this go? We're very conscious of climate change. I'm sure all of you have come in tonight wanting to understand how fusion can join in. I think the main message from me is fusion does not do it all. And indeed, fusion will not really be here commercially in 2050 and in the years up to 2050. So we will not contribute in any meaningful way to reaching net zero, which of course is what the whole world is and should aspire to do. But we certainly will help contribute with renewables, which will grow for sure, with, I do believe, nuclear fission, to take out the worldwide reliance we still have on burning fossil fuels at the minute, and fill that gap that I've filled in with the arrow there. So very much fusion will work with other sources. And I think if those three come through, that's the best we can hope for to generate you know, an electricity market in the future that will be low carbon. That's of course what we all want. I'm going to leave you not from what I've been saying, but from two far more impressive figures in the world of science. Of course, the very sadly lately departed Stephen Hawking and Brian Cox. And they were asked this question some years ago from The Guardian. And I should point out, we didn't pay them to say anything here. Brian Cox has always been a huge proponent of fusion. And they answered this, that nuclear fusion will provide an inexhaustible supply of energy without pollution or global warming. And this last sentence is really hopefully sums up one of the key points I've made tonight. We know how to do fusion as physicists. We know how it works. It's now an engineering solution that's within our grasp. All of the work I'm describing that we're doing in those engineering areas is really key to putting it on the grid and making it work, so that one day you'll turn your lights on and fusion will be driving your electricity. Thank you so much. I'm going to leave, hopefully, the screen up on that final rather inspiring quote, and hope I've got a few questions to answer. Thank you very much.
Thank you, Chris. I always really enjoy hearing talks from you and your colleagues about fusion energy. Really, really inspiring. And I think, you know, we have a lot to thank Arthur Eddington for.
We certainly do. We certainly do.
We did have one question come in quite early on in your presentation, Chris. Someone was asking, how does the ITER/JET toroidal reactor design compared to the very complex geometry of the Wendelstein 7X that Germany are pursuing? Someone
who knows their fusion stuff. There are, and I've alluded very briefly to it tonight, there are other ways of looking at fusion. Within the magnetic fusion community, which is what a tokamak is, using powerful magnetic fields in as the question suggests, a more uniform geometry. There are devices called stellarators being looked at around the world, less intently, but nevertheless in Europe, with a major machine called Wendelstein. And the idea of a stellarator, which looks, if I may be so bold, as something that Salvador Dali designed, the twist of the machine, the twist of the vessel is matched to an optimum set of field line structures inside, and every coil and every twist of the vessel is unique. So every coil is not just a simple D shape or a ring, it's now a unique geometry. There is a very famous quote from the world of fusion, which says that Stellarator is easy to operate and a nightmare to build, and the tokamak is the other way around. I've just forgotten which way around it was. So Stellarators are designed to run much more steady state and in a much cleverer way. And Europe is quite frankly saying, look, we've got a big tokamak program, and now we've got a big Stellarator program, and at some point it will have to make a decision on which it pursues. I see that as a real positive. Some of the private fusion companies are looking at very different technologies, and two of them I've alluded to tonight. And the whole other field I've not even spoken about is laser-driven fusion, which is being looked at a lot in the US at the National Ignition Facility. So I think it's a real positive sign that there are many other routes being pursued towards a fusion power station. And quite frankly, I hope they all work, because that will give us a whole broad range of technologies producing fusion on the grid in the future.
Thank you, Chris. Another question has just come into our Q&A box from Rupert, who is asking, is any work being done on cold fusion?
Cold fusion, we don't. Cold fusion is a very difficult question for me to answer. Cold fusion has been around for a long time as a concept. It really gained huge prominence actually just before I joined the authority. I joined in 1990. This is what you look like if you work at Cullen for 31 years, by the way, everybody. 1988 was the big cold fusion news story when Fleischmann and Pons claimed that in an electrolyte solution between two palladium electrodes, they were starting to see some fusion energy and neutrons being produced at room temperature. Never mind having to heat your fuel up to 10 times hotter than the sun, they could do it at room temperature. And of course, that at the time appeared to be an enormous leap forward. These experiments were attempted to be recreated, not actually by us, because that would have looked odd, but certainly at Harwell did amongst other labs around the world, and they couldn't be. I don't think this was ever done disingenuously. I just think results were mistakenly analysed. Cold fusion is still looked at various labs around the world, not by the big ones, I would say. And the one at the minute is bubble fusion, looking at sound waves imploding and compacting bubbles within a liquid and claiming fusion will come out. Very difficult to say exactly what's going on. Most of the scientific community would argue there is some interesting chemistry going on, but it's not fusion. And I think my observation with it is whenever I've seen any cold fusion claim, is that scaling up to something economic, gigawatts on the grid, will be pretty impossible for most of what I've seen. But it is still out there. We don't look at it ourselves at UKAEA.
Thank you, Chris. Another question regarding the other companies that are sort of coming into the sort of fusion sphere now. So companies such as First Light and Tokamak Energy. How do you see them contributing to fusion development? Could they accelerate the journey to net zero?
I think what we've realised in the last few years, and certainly as we've built our technology facilities, is we are a national public laboratory, publicly funded, and we have a broad range of work looking at the fundamentals. We do recognise, however, that it won't be us building the power stations. That will be industry and operating them. And private fusion companies do have more flexibility to explore new ideas and look at new things. I think clearly, we're not going to be able to share everything that each other does, but it's very, very powerful that we can all work in parallel towards meeting the goal of putting fusion energy on the grid. And as I say, I don't get hung up on what ends up being on the grid. If several different devices and methodologies and technologies work, then I think that's a great thing. So it's very powerful, I think, for this cluster to start to come together, supply chain. And what I didn't mention was Oxford University does an awful lot of work in materials research and plasma physics for fusion with us, as well as many other universities around the UK. So I think that's a real positive. I can't look into the future and say how we'll work together, but I think it's absolutely essential that we do with the nous of the private sector. With the work that we do behind the scenes as well. I think all of these really have to work together to make it succeed. So collaboration is key. Absolutely, absolutely.
So we've got another question here that's taking nuclear fusion away from just creating electricity. Do you think that nuclear fusion will play a big part in other areas, for example, colonising other planets in the future?
Okay, I did wonder where that question was going. I'm not looking in deliberately, I'm waiting for them blind. Let me answer in a more terrestrial way first. We certainly could imagine that fusion electricity or fusion energy could be used for desalination. It could be a key part of a hydrogen economy. And of course, electric cars, etc., would need clean electricity, of which fusion would obviously be able to contribute. But I don't think we should get hung up on Earth with electricity. There could be all sorts of other uses directly for fusion energy coming out of one of these power plants. The question alludes to how fusion might be able to power space travel in the future. And most science fiction films have fusion as a power source of some kind of spacecraft. The Millennium Falcon, most notably in one of the Star Wars films at least, is portrayed as having a fusion device. Fusion needs very little fuel to work, which means that you wouldn't need to lug around like a chemical rocket does, all of that liquid oxygen, liquid hydrogen. You would be able to travel very much further distances in space, theoretically, he says, with some kind of fusion power source, and you would be able to carry fuel much more effectively because you need so little fuel. Saying that, we're a long way away from a fusion-powered spacecraft, and we certainly aren't looking at that here. We have our hands full trying to develop and play our role in developing this for the grid here on Earth. But I think it's fair to say fusion is a good candidate for future space travel, but I'm not going to get drawn into postulating and future gazing any more than that.
Well, let's future gaze in a different way. Tony has asked a question that I actually wanted to ask you as well. So it's always been said that power from nuclear fusion is 30 years away from becoming operational. So how realistic do you now think your current timescales are? And could we have commercial fusion electricity in the next 30 years?
It's the question I expected, and thank you. I've been at UKAEA for 31 years, and indeed we were talking about 30 years when I joined. I think the difference now, the reality is that this increase in focus in doing it economically, frankly, we could go all guns blazing now. In the next 10 to 15 years, we could build a fusion power plant. We could recognize it wouldn't be in any sense economic, that the materials wouldn't be right, that we wouldn't be able to remotely maintain it. And we could probably put something on the grid pretty quickly. It would not be commercial electricity. We would learn a lot, but it would be a very difficult machine to be able to fund. So I think it is very realistic to be talking about commercial deployment in the latter half of this century, in the years 2050 onwards. If you chucked much more money at it, could you do it quicker a bit, but you wouldn't halve it? So I think the answer to the question is yes, we are much more confident now. We're looking at it in the round. We're looking at the engineering challenges and the technology, the things that make a power plant realistic in the future. And I think that's what's different from when I joined. Even if I just go back 7 or 8 years, we didn't have active programs in any of that. Now we do. Robotic maintenance, materials, working with industry much, much more than we did just 7 or 8 years ago. I think that shows that we're really serious and we're plotting a time route to fusion. Do not hold me to it in 30 years, please. But I think if we're not there, we'll be very, very close.
So what do you think is the biggest material or technology improvement that might change the trajectory of the commercial path?
I think for me, and this is a personal view, because I think the challenges I put up earlier are all really big ones, but the biggest one for me is the materials. Can I find a material that is structurally sound to make my machine out of, that withstands these ridiculously fast neutrons? They're 10 times more energetic than neutrons from a fission reactor. And 10 times therefore more damaging, that doesn't get too active by absorbing those neutrons. So I don't have a huge legacy at the end to deal with. We have that within our gift. If I can find those magic materials, that will be the big breakthrough moment, I think, amongst others, that will really make people sit up and think, yes, this is the way to go. But all the others will play a role. But for me, the biggest one, if I had to choose, were the materials.
So some big challenges ahead.
Certainly keeps us busy.
Definitely. Oh, we've just had one question come in very quickly. We've got a couple of minutes. It's the one you thought might come in, Chris. Has your funding been affected by Brexit?
I kind of thought I wouldn't get the Brexit question anymore, but we have had, since the decision to leave the EU, some uncertainty. We are part of Euratom. I don't wish to get too technical, which is an atomic treaty connected to the European Treaty. And we were delighted, and I can remember the Christmas Eve very well, last Christmas Eve, when the deal was all signed, or the 23rd or whenever it was, that we have chosen to associate to Euratom. So the UK is still a member of Euratom through association. That means we remain able to operate JET. It crucially means we remain within the ITER programme through the EU. Materially, our funding has not been affected, but it's taken some years of work to get to that point, and we're delighted with that decision. And indeed, UK government are being immensely supportive with 200 million towards the STEP programme that certainly 10 years ago we would never have expected to have gained. So our funding overall is increasing, and the impact of Brexit has been minimised. So we're absolutely delighted about that.
Oh, that's really great to hear. So we are running very short on time now, so I haven't got time for any more questions. But thank you, Chris. It's been an absolute delight to talk to you. But that's it for tonight. Always a pleasure to be talking to UKAEA. But all that remains for me to say is thank you, Chris. Thank you to the audience, and good night.
Thanks very much.